you want to understand electrostatics and how we can build up charge and get some of the phenomena that we saw in our mini lab last week, you really need to start with understanding the atomic model. In chemistry class, there are different models that you learn, but the basic one would be the one with a nucleus in the center and this cloud of electrons, often referred to as being in valence shells. And when you look at the periodic table, you see this relationship between these free-flowing electrons that can be transferred. And that's what I want you to be thinking about when we start talking about the atomic model. So let's look at an atom in particular. Let's look at a helium atom. Helium has an atomic number, if you look in your periodic table, of 2, which means it has 2 protons in the nucleus. And so if we draw a picture, you would have your nucleus, which has your 2 protons. Now you also have these things called neutrons. A proton carries what we determine to be a positive charge. So sometimes you'll see it listed as P with a plus next to it. A neutron does not carry any charge. It has mass in the nucleus, but it doesn't carry any charge. It's neutral. So to balance out the charge, you also have these really tiny little specks out here that we call electrons. And an electron carries a negative charge. And so we call that E to the negative, right? There's another electron. And what I think is really important to think about and understand with these atoms, and really any atom, is the scale of these electrons to the nucleus. And a good example is to think of the link as a football stadium. If this atom of helium was the size of Lincoln Financial Field, and this nucleus was at the 50-yard line, it would be the size of about a walnut. Whereas these electrons would be like a speck of dust in the far seats of the upper deck. So there's all this open space, and these tiny little electrons flown around this nucleus in kind of a cloud at various levels. And as a result, they're very easy to be moved around depending on the atom. So we need to understand that electrons, because they're in this cloud around the nucleus, can easily be moved both within the atom itself. So you could get all the electrons on one side, or they kind of spread out, but they have this freedom to move around. Or even transfer to other atoms in a material. So these electrons can actually be shared across the atoms of a material. And when you get this exchange of an electron, you get this concept of a charge. A charged atom, or a material of atoms, is simply a state of imbalance. And that's an imbalance of the protons and electrons in the material. All materials and all objects in our universe want to find balance. Right? This is a pretty universal theme in science. And if you think of it that way, these atoms, or any material for that matter, wants to have no charge. And as a result, you see this movement of electrons between materials and between atoms. And that movement, or you can think of it as a displacement, of these electrons is what creates a charge. The important thing to understand is the atoms themselves don't move. So when you looked at all those demonstrations and you had the wool being rubbed on a piece of plastic, the material, the wool isn't actually transferred to the plastic, nor is the plastic going to the wool. However, the electrons of those materials are being passed back and forth. If the actual wool was being transferred, you would be considering the actual nucleus of the atoms to be moving. But that's not the case. These nucleus of the atoms themselves are staying within the material unless you really rub it like maybe a pencil sharpener or a pencil eraser. But since the nucleus doesn't move, we really need to understand that protons do not move. It's the electrons that are doing all the moving. They are these wispy, light little particles along the fringes of these atoms, and they're really easy to sweep away via friction, and that's what creates this charge buildup, right? So if we start talking about what we would call a negative charge, that would be a material such that it has gained extra electrons. So we would say it has extra or excess electrons than it would normally have if it was in a state of balance. So a negative charge would be excess electrons in a material. On the flip side, you can get a positive charge in a material. Now, a common misconception would be, well, that would just be extra protons. Well, since protons can't move, we actually get a positive charge by removing electrons, right? So a positive charge is caused by having a missing number of electrons. We could create a positively charged helium ion, they call them ions when you think of the atoms themselves, by removing one of its electrons so that it has two protons and only one electron. We would say it's ionized. You could also give helium one extra electron. It would have 3 to 2, right? And therefore have a negative charge. And some atoms, based on their material properties, are more willing to give up or receive electrons. And most atoms, if you look in their normal state, are neutral. Or we would say they're uncharged. This simply means that the number of protons in the material is equal to the number of electrons. And this is where most materials want to be, but due to other factors, friction with other materials, what's happening in their environment, you get this situation where electrons can temporarily be moved away from the surface of that material towards other materials, and we get that charge buildup. Now, when we're talking about charge, charge can actually be quantified. Just like we can measure distance or time or velocity with a number, and we have a label of a unit, we can measure the amount of charge on a material with a unit and a label. And that unit is called the coulomb, named after a scientist. And we use capital C as the abbreviation. And a coulomb is a standard unit for charge. It's the metric standard. And so if I've added one electron to an atom, and it has one extra electron, it therefore has an extra amount of charge, and we could quantify that. In fact, one electron is equal to a negative charge of 1.6 times 10 to the negative 19 coulombs. And on the flip side, if I took an electron away, that material would now have one less electron than it wants to normally have, and therefore have a missing electron and be positively charged. And therefore, you can actually look at a proton and quantify what it must be. Right? If a proton and electron balance each other, then a proton must be positive 1.6 times 10 to the negative 19 coulombs. And it turns out if I take the inverse of these numbers, I can find the number of coulombs in an electron or in a proton. Right? So if I take the inverse of 1.6 in my calculator, 1.6 second e to the negative 19, and I raise it to the negative 1, right? I really just flip my conversion factor, and that's the number of electrons or protons in 1 coulomb. So 1 coulomb is equal to 6.25 times 10 to the 18 electrons. Right? And since protons have the same charge as electrons, that's also the amount of charge, the number of protons that would create that much charge. All right, so this is the number of electrons or protons in 1 coulomb of charge. It turns out a coulomb is a lot of charge. When you talk about a lightning strike, that's in the scale of single-digit coulombs. So a coulomb is a lot of charge, and as a result, we end up dealing with really small amounts of coulombs. And so I want to take this chance to review some metric prefixes, because we're going to see them a lot in this unit, because we're going to be dealing with really small amounts, really tiny amounts of charge. So if you recall back and you think of some of your metric prefixes, well, I'll kind of deal with the small ones at this point. The ones you need to know for this unit from a review standpoint, you typically are going to have your base unit. Right? That base could be meters, could be seconds, could be grams. Right? In this case, the base would be coulombs. And that base, if I want to convert to the same base, well, you multiply by 1. Right? It doesn't change anything. Right? The ones we need to know as you get smaller, the first one you guys should be familiar with is centi. And I hope you're thinking cents as in dollars and cents. A cent is 1/100th of a dollar, which is the same as 10 to the negative 2. Right? 1 over 10 squared is 100. 1/100th is what C represents. Most of you guys know about milli, like millimeters. Well, that's 10 to the negative 3. It's 1/1000th. So a millimeter is 1/1000th of a meter. There are 1,000 millimeters in a meter. Just like there are 1,000 millicoulombs in a coulomb. From here, they typically jump up in factors of 3. So let's go from milli. The next one would be 10 to the negative 6. You go to micro, which is that Greek letter mu that we use for friction. Then you have nano, which is a little n, that's 10 to the negative 9. And the last one you might run into is pico, P-I-C-O, which is 10 to the negative 12. All right, and so these are just basic metric conversions that hopefully shouldn't have any problem converting. We'll do an example here in a second. But because we're dealing with charges on the scale of really small amounts of coulombs, we're going to typically see charge amounts measured in smaller units. So let's look at an example, and I'll let you guys solve one. This is a typical problem where we deal with charge. So let's say we take a balloon and we rub it on our hair like we saw in the video last week, right? And as a result, that balloon, due to the friction with the hair, is actually going to pick up electrons from the hair. As we'll learn later, hair will give up electrons to rubber, right? So that balloon, once it's rubbed on the hair, it's going to pick up extra electrons and therefore will have a charge. And if we were to quantify that charge, we can say maybe it has a charge of negative 40 NC, which is nanocoulombs. So the question I have for you would be, if that is its charge, well, that charge comes from having extra electrons. Well, how many extra electrons are on that balloon? So I'm going to leave you to work on this individually for a couple minutes, and then I'm going to put you guys in groups. All right, and as a hint, I want you to think about solving this problem as a unit conversion problem. All right, and if that's the case, hopefully you're thinking, hey, fence post, we've done unit conversion before, so good little review. All right, and so I'm going to zoom back here and show you the stuff you need to know. All right, there's our conversion factors. We know how many electrons are in a coulomb, or coulombs in an electron. And there's our metric prefixes. And I want to know, a balloon carries a charge of negative 40 nanocoulombs. How many extra electrons are on the balloon? All right, so I'm going to give you a minute, let you guys break here. And I want you to try to solve this problem, and then we'll break you guys into groups.